Hey, Emily, I think I forgot to reply to your email, so I'll do that after this class. Sorry, I read it, but forgot to reply. I just realized now. So today we'll basically finish the part about integrating wind turbines into the system. So we'll finish looking at low voltage right-through. Then we'll start looking at solar and storage after that. Okay. So as a recap, what we talked about last time was we have wind power, right? We have wind power. And historically, when wind power first came on the grid, this was treated as negative load. Okay, so historically, this was just negative load. So which means you basically generate how much you want to generate. And it's up to the rest of the system to balance the uncertainties in wind power. Okay, so in the 80s and 90s, if you have wind turbine, you're not carrying any of the, you're not performing any services to the grid. You're basically just coming and generating power, and you can come and leave whenever you want. Then last time we had a big blackout, right? So this is after the big blackout in 2003. Then we start requiring wind turbines to act more like synchronous generators. Okay, so the requirement after 2003, because of big blackout in the US, then we're start to basically require they need to act more like synchronous generators. So they're not just negative load anymore. They can just come in, generate however much they want. They have to provide things like reactive power. They have to provide some voltage control, right? They have to, stay on for a certain amount of time. So a lot of, innovation happened along that time. That's basically why we have a lot more type 3 and type 4 turbines, is because there's sort of requirement from the regulators. All right, so then, basically these codes gets updated every time we have a big, blackout or big event on the system. So I expect that after the California blackout last year and the Texas blackout this year, we'll see an update again to the wind turbines. They're probably going to be required, to even act more like firm generators. So we may see some new designs after this year. There may be some more requirement after this year. Okay. But the main thing from the last major update of the requirement of the code is they have to support the grid in various different ways. Okay, they have to stay in the grid for various certain ways. So basically, this requires. So last time we covered that wind turbine. So we have a wind turbine. We have times from milliseconds to seconds, all the way to, let's say, hours. Okay. So previously, if there's any fault on the system, let's say if you have a fault for a millisecond, and then it's okay for the wind turbine to just disconnect from the system, right? Just disappear from the system. Nowadays, basically our requirement for wind turbine is wind turbine must stay connected and operate through all these different time scales. Okay, so we have sort of different mechanisms for wind turbines. Okay, so there's different ways that the wind turbine has to operate, and sort of must work with the grid over different time scales. Okay, so this class will focus on one of them, basically called low voltage right-through. That's sort of one of the more important requirements for wind turbines. But before that, we're going to again take an overview of all the different ways that sort of the uncertainty of wind come into the system. So if you look at the wind turbine operations, basically there's a lot of time scales, and we need to consider all of them in a system, right? The system operator really needs to consider all of them. So if you look at the time scale from milliseconds, then really the issue is stability, right? So does your wind turbine, is stable, right? You want nothing to blow up in a few milliseconds. So this is really, for milliseconds, we care about stability. And this is what we'll talk about for the first half of today's class as low voltage rising. Can you survive and can you stay connected to the grid for a few milliseconds? Then if you go longer in the time scale, say from seconds to minutes, then we care about things like frequency, voltage. Can you provide some frequency regulation to the grid? If you lost a generator, can the wind power produce more power to help the generator? Then going longer in time scale from minutes to hours, we want to know if you can follow the load. They want to understand how to do scheduling, right, in the turbine. Okay. So today so today if you look at so this is a time scale, right? So this is the separation in time scale of all the issues about integrating wind into the grid. And if you went to today's seminar, right? So if you went to Professor Calloway's seminar this morning, you heard about different timescales and different stability issues. So that's very much related to what we're going to talk about today. So this is a way to divide up through, think about the wind turbines through different timescales. And another way to think about integration, is to think about what device or what kind of operation we're doing to mitigate some of these issues. Okay? So for this way of thinking, basically, we can divide things into interface, the planning operational, and grid control. Okay, so what interface this means is this is really just the converters on the turbine. Type 3 or type 4. Okay, so interface means how you interface with the main grid, right? And we do this in type 3 and type 4 through AC, DC, DC, AC converters. And so this is mainly local to a turbine, to the sort of the converters of a turbine. And this has things to do with fault right through, right? So this is, so if you see a fault on the grid side, how well can you survive the fault and still be operational? This has to do with reactive power. Again, for us, our reactive power is provided by the power electronics, essentially, by the power electronics. So this is a local issue of can you provide reactive power? And then we have things like ramp rates, right? So how fast can you ramp the power up and down? That's again depends on the interface, on the converters that we have, in the turbine itself. Okay, so this is mainly respect to a single turbine, right? So this is how you design a single turbine. Then the other two have to do with the bigger grid, with a bigger system, has to do with the bigger system, right? So for example, in planning operations, we need to think about wind uncertainty. Right? So wind uncertainty really does not impact the operation of a single turbine. Right? The turbine, is powered by wind, and there's more wind, you produce more power. The less wind, you produce less power. That's really not the issue there is not a single turbine, but this has to do with planning and operating other resources in the grid. So we're going to think of this as a operational issue, right, with respect to others. Similarly, we have balancing. This is how does supply equal demand, and we have transmission. Okay, we have transmission. Right? So these have to do with the sort of the larger grid. Right? It has to do with larger grid issues. Then grid control issues. This is in a shorter term than planning operation, right? But still it impacts the whole grid. So your own turbine may very well be stable, but we still want the larger grid to be stable. We integrate the turbine into the system. So this has to do with things like dynamic stability of the grid. Things like load following. So this is automatic generation control and things like that. Okay. So today in our class, we'll mostly focus on a single issue. We'll look at fault rise-through. So we're going to still look from a single turbine's perspective, right? We've been taking this perspective for most of the class. We're looking at a single turbine and how do we design this turbine, how to understand this turbine. And fault rise-through is still along that line. Right? So we're going to think of a single turbine, how to do fault rise-through. The others requires a different process. You have to think from a system level process. So if you're interested in the other issues, you can take classes like 454 or 554, where we really explore sort of the system side of things. But for today's lecture, we'll still look at a single turbine. We'll look at how, if you're a single turbine, how do you operate when there's a fault? Any questions for this? About different integration issues? About different timescales? All right, so if not, let's look at low voltage rise-through. Okay, so this, if not, let's look at low voltage rise-through. So the low voltage rise-through comes from, so we call it low voltage. This terminology comes from the fact that the fault that typically happens is that the fault that shorts the grid side. Okay, so the fault from a turbine's perspective look like the fault you were shorting the grid. So if you remember before, a low voltage fault is I have a generator, I have a wind turbine that's generating, right? So normally this goes out to the grid. And this fault, what happens if there's a fault? Then this looks like a ground, basically. As if you're grounding this turbine. So when you have this kind of fault, basically, as what happens is the active power, the electrical power output drops quickly. Okay, so the electrical power output tends to drop very quickly if you have this sort of fault. Anybody have an idea of how much in proportional? So if I have a fault, right? So why does the output power drop? If you have a turbine that's operating, and suddenly there's a fault and it appears so your voltage drops as the output drops because it's as if you're being grounded. Any idea on what scale this drop is? So if your voltage goes down, typically how much does your power go down? Right, so how does power scale with voltage? Well, remember, so I have a voltage, my voltage drops. Then how does my power change if I have a change in voltage? Right, so in this case, if you have a power, right, so the power changes roughly proportional to V squared. So we have a voltage, then the power in my system drops, so I have voltage V, power is roughly V squared. So this drops quickly, meaning this decreases roughly by V squared. Okay, so you have a voltage magnitude that drops. then power also drops because it drops like the square of the voltage at the output. I may remember what happens if your electric power drops from previous classes. So I have a turbine, right? I'm spinning, I'm generating power, and then my electrical power output drops. Then what happens to the rotors? Right, so the James says in the chat, right? So my rotor speed increases, right? My rotor accelerates because mechanical power has to go somewhere. So this accelerates the rotating mass I have in my system. Right, so the rotor accelerates, and this causes the turbine. This may be unstable, right? This may create some instability in the turbine, and then what happens is this will typically trip the overspeed protection relay. Okay, so normally we have some relay in the system, and the relay detects how fast the rotor is going and may trip this. Okay, may trip this relay. So let's say if this relay is tripped in the system, right? So let's say we trip the relay, and then the system goes offline, right? So when we trip a relay, it means the turbine disconnects from the system, goes offline. And then what happens if you connect the turbine online? Right, so let's say the fault happens, you trip offline. Then let's say now the fault has cleared in a few seconds, right? Let's say the fault clears in half a second. Then you connect the turbine again to the grid. Then what happens if, let's say you have an induction machine, it stops. Then you connect the induction machine again to the grid. So when you start an induction machine, let's say this is type 3. When you start an induction machine, how does the starting current compare to the steady state current? Which is larger, the starting current or a steady state current for a turbine, for induction generator? Right, so Kelsey says the starting torque, right? So we cover this, right? This is also covered. So this is the starting torque, starting current is large for induction machines, right? So it takes a lot of current to get it started. Once it reaches steady state, it's sort of smaller current. So what this happens if you trip the relay, so let's say you have a fault, you trip the relay, that it goes offline. You clear the fault, you can reconnect the turbine. But then what happens since the turbine, now the induction machine just starting again, right? Starting from sort of zero, starting. Then the starting current is very large compared to the steady state current. So what this does, this creates another shock in your system. Okay, so this is another transient introduced to the system. Okay, so you may have cleared the fault, but now you have additional transient because now you're reconnecting this induction machine. So that may lead to other faults actually. So you clear the fault, you start the system, now you suddenly have a lot more current going through it because you're restarting your machine. So then from some other protection devices perspective, looks like additional fault has happened. So that's a drawback of just just tripping the turbines offline if anything happens, right? So this, if you start them again, this creates a large transient, basically. This looks like another fault. Okay, so if the wind turbine is large, especially, and you connect it to the grid, then for a grid that just recovered from a previous fault, we just cleared the last fault. Now there's a lot of current coming again. That's create other problems in the grid, right? So you don't really, you don't necessarily want to just kick your turbines offline whenever you see a fault in the system. So now that's the reason why we call it rise through, right? That's the reason. So we're gonna do low voltage rise through, because the idea is if the voltage is low, means there is a short ground fault. We want the turbine to rise through to have the machine not completely decouple from the grid, and then have to restart the machine. Right. So again, repeating this, historically, we disconnect the machine to protect against overcurrent and overspeeding. But then for large turbines, so if your turbines are very large, right? So small machine is fine, you can absorb that. But your turbine is large, this actually may amplify the fault. Or amplify the disturbance. Because now when you reconnect, you act like another disturbance, right? So you may create a bigger disturbance than the original was. Okay. And then this could destabilize the system. Right? So before the new regulation in the early 2000s, this was actually observed. As often as not the fault that disturbs the system. It's for the reaction to the fault that destabilizes the system. Okay, so it's not necessarily the fault. The fault is not the primary issue. It's sort of because we're reacting to the fault by just disconnecting everything, that is causing problems, causing more problems in the system. So then we have this low voltage rise through requirement. What this requirement does is you have to, basically the turbines or the wind power plant has to stay online. Okay, so it has to stay online. It cannot disconnect just from the grid. And you're required to provide okay, so you have to use the power electronics in the turbines to provide some voltage support, right? So you have to provide some voltage support, and you should not, again, you should stay connected, and actually it's up to you, try to sort of prop up the terminal voltage of the turbine. So for this, then, right, so if you look at the faults in more detail, so this is a requirement. Okay, so this is a design requirement. You have to do this. So nowadays, you want to install wind power, these are required. You have to, so you have to be able to reset to pre-fault values. Right, so if the fault is clear, you have to reset to it. You have to reset there. Then so this is a requirement, and then there's some other requirement. So also we're starting to require that increased reactive power support. Okay, so also it's required to do increased reactive power support. And this, if you look at the turbine technology we had going from type 1 to type 4, right? This is quite a long way. In type 1, all you do is you consume reactive power. Type 2, you consume reactive power. But nowadays, if you're a turbine, you have to be able to generate reactive power. Okay, so it no longer suffices to just consume reactive power. Okay. So that's quite a long way where they have come. Okay. So to sort of really understand, the key things in low voltage rise through, right? The key things in low voltage rise through is basically you have the requirement that you have to stay online. You have to stay online. But of course, you cannot be required to stay online indefinitely. Okay, so you can be required to stay online. The key question is how long should you be required to stay online for? Right? It's unreasonable to have a generator that's not connected to the grid or that sees a fault to stay online, say for 20 minutes, right? That's not reasonable, because if you're getting mechanical power to stay online, that power has to go somewhere, right? So the key question becomes, once we figure out that we want the turbine stay online, is figure out how long they stay online for. Okay, so you cannot require them to stay online for arbitrarily long. That doesn't make sense. But then they should not cut off right when a fault happens, right? So for the next, we want to understand, if you're required to stay online, how long should you stay online? Is it a millisecond? Is it a second? Is there something in between? So how long should we be in the system? Any guesses at this? So you think you're a turbine and you see a fault, right? So think of the fault as I'm grounding your terminal. Any guess how long you have to stay online? Any guesses, right? So what's a reasonable number that you think a turbine can stay online for? Any guesses? Is a second reasonable? Think back to the calculation we did, right? When we're calculating basically the resistance, right? How much power you have to dump through a resistor to when fault happens. Same ideas, how long you have to do this? Can you stay online for a second? Right, so if you look at all the calculation we did before, we're basically computing how much energy you have to get rid of in tens of milliseconds. Okay, so requiring a turbine, we said low voltage ride through. The ride through is actually not super long, because again, you cannot keep generating mechanical power and thinking that you can always dump the power, right, somewhere. So this requirement actually will turn out to be, this is 9-10 cycles. Okay, so this is 9 or 10 AC cycles, right? So an AC cycle is 1/60 seconds. So this is about 100, on the order of 100 milliseconds or so. This is sort of the length of time that right now you're required to stay connected to the grid. Okay, so there's so 10 cycles is 1/6, so this is 150 milliseconds, right? So that's a good number to have in mind. That's how long, if you run a turbine, right? You have to be able to survive the fault in the system, right? So where does that from? So a little bit more detailed. So let's look at some IEEE standards on this. So there's a lot of standards. There's quite a number of standards that governs, right, this type of times and exactly the standards you have to follow. So if you look at the reclosing action, this is basically says that this, if a fault happens, this is what you do to try to clear the fault. Okay, this is what we try to clear the fault. This basically what this standard says is, if you have a generator here and you have a fault, right? And you have a fault. You have a fault on the line. Let's say there's some fault, some sort of transient fault on the line. Then what happens is now the breaker opens, right? So now so what the system looks like is you have a little breaker here. You have a little breaker here. You have two breakers at two ends of the line. Okay, so if there's a fault, the breaker will trip. Right, so there's the, okay. And what this reclosing action says, if there's this kind of fault happens, you reclose from the right to left. Okay, you reclose from right to left. Right, so you reclose from right to left. So when you reclose, you have to reclose. You have to close switches in this direction, you have to create close switches sort of far away from the generator first. Let's close this first, because you want to avoid doing damage to this generator, to these turbines. So that's why our fault is not too short. Okay, so the question is, why do I have to stay, let's say, 9 to 10 cycles? When can we not clear a fault in a single AC cycle? Right? Why is it? Why does a fault last 0.15 of a second or so? Right? Why does it have to last hundreds of milliseconds? As if there's a fault and something trips, then if you're close to a conventional generator, you actually want to give the generator some time before you reconnect the generator to the rest of the system. So this controls how fast you can basically clear a fault. Okay, so clearing fault means restoring all the connections in our system. And because traditional synchronous generators require some time to be able to reclose the switch close to them, so then you have to live for 9 or 10 cycles, right? So that's why we cannot reclose everything in 1 or 2 cycles. Okay, so this is a trading off. So this is putting sort of more requirement on the wind turbines, because we need to take care of the traditional conventional synchronous generators we have in our system. Okay, so because their requirement that the wind turbines has to take some time to close their fault. All right, so then if you look at this, then the actual fault, sort of the reclose action, right, goes something like this, right? So if you want to minimize the closing speed, then the reclosing action is sort of very deliberate. It's not that fast. You have to wait a little bit. Okay, so this is, we basically have sequential closing. Okay, so a little bit on sort of how the faults are cleared is we have sequential closing. Okay, so we'll close from the remote end of a line. Okay, so we'll close from sort of again, if we have a generator and you have a bunch of breakers on the line, then you close from this direction. Okay, then you close from the far end of the line, right? Because you don't want to close too quickly to the close to your generators, but you still want to clear the fault by successively closing. So you go from the right hand side, right, from far away, you keep closing to the generator. So this is sort of the normal sequence of closing. This sort of protection sequence we have in our system. Okay, so then so graphically what happens is, right, so quite simple, is if you have a generator, you have two circuit breakers at both ends. During a fault, right, during a fault, this guy the remote end will try to close first. And maybe successful, maybe not. But anyways, it will try. And then if it tries and you cannot reclose, then that means we stop. Okay, so you never actually reclose the one close to the generator. So you close from remote end. You basically wait and see if the fault has cleared. If the fault hasn't cleared by the time you try to reclose, then you stop the operation, right? When you stop trying to reclose this. Otherwise, if you see there's a fault, both breakers open, but then the fault may be clear. And the sort of standard example for this is a lightning strike on the line. Okay, this happens a lot more often than you may think, right? Because there are just so many lines. So it's not atypical for some line to have a short fault. Either there be a lightning strike or something gets shorted very quickly, so you have a fault. Both things open. Then the right-hand side will try to close. If it is able, then the left-hand side will close. And this is a sort of dedicated sequence. Okay, this sort of dedicated sequence. Right? Any questions about this closing sequence? Okay, so one question that we may want to think about, right? Question for you guys is, how does the breaker know where you are? Right, this seems to be, requires a fairly synchronous operation of the breaker. Right, one has to open first, the other has to, both has to open, one has to close, and the other has to try to close. So if you're just a breaker, how do you know this? Right, you're breaking the system. How do you know, when you should reclose and when you should not? Any ideas how this is currently done in practice? Any ideas? So how do we program these breakers? How do we, right? So we said go from the furthest end, right? So set says SCADA, right? So SCADA means, you take measurements, you communicate the measurements, and you feed back to the control center, and you design that way. That's actually not what's happening today. Right, so this question, a little bit of a trick question. What happens today is actually all these things are hard coded into the breaker design. So if you could look at the breakers today we have in our system, when you put it into the system, you have to know where it is, and you hard code a timing rule into the breaker. There's not much real-time measurement. When you put the breaker in, you have to set in the breaker manually. You're the second in the sequence. So if you measure a fault, you wait for 0.1 milliseconds, then you try to reclose. Okay, all of this right now actually set by hand. So when you go in and install these, as there's a little programmer, you program this, there's not much real-time measurement communication going on in this sort of protection. So that's something to be aware of. A lot of issue about wind and to a larger extent solar and storage is actually dealing with the protection scheme we have in our system. Because this protection scheme was, right now is mostly manually programmed. So just a PLC, yeah, kinda, so that's right. So it's a sort of very simple controller. It's very simple controller, right? So that's sort of something, as a future, something you want to keep in mind is how do we deal with this sort of protection device? It's actually quite a frustrating thing we have in practice, actually. So a lot of effort actually is going into how do we update protection? How do we not set them manually by hand when we install them and not change them for 20 years? And second is if they're set this way, how do you get your wind and solar and storage to play nice with this sort of protection scheme? Okay, so that's something to be keeping in mind of. Right? So that's something we'll see a little bit more if when we talk about solar, as this kind of protection issues we have. But for wind, the way we solve the protection issue is we tell the wind turbine, basically, to stay online. The reason you have to stay online is you're waiting for the other breakers to do this kind of dance. Right? If they're trying to do this kind of dance, and if they're successful, then by staying online, you can recover the entire system. Okay? Right? So that's the sort of wind turbine's job, to wait this out, wait out this process. So if they don't close, then after 10 cycles, you can just trip offline. That's fine. If they do manage to close, then you should be there when the system is reconnected. Okay? So this is the goal of that. And then our objective is to ride through, right? So ride through this low voltage. You ride through this faults, and you have to stay on for the nominal or for the normal clearing time. That'll be 9 or 10 cycles that we have in our system. Okay? And this is mandated by this FERC order. right? So this first order basically says, for 9 cycles, you have to be there. Okay? You have to be there. If you're not there, then afterwards, if they figure it out, then you basically get a fine, right? That's your problem for tripping offline. And you have to survive with a fault that creates a voltage as low as 0 volts. Okay, you have to survive basically as if you're connected to the grid for 9 cycles. And then if, of course, if it lasts any longer, then a wind turbine can trip offline. Wind turbine can feel free to trip offline. And all this is quantified by something called a low voltage rise-through requirement. So what this low voltage through rise requirement does is goes in and determines, for example, 9 cycles, and determines exact amount of voltage support you need and all of that. So every system we have, so all the systems in the US will do this kind of study. And after the studies, they will publish basically the sort of requirement, right? So this is updated every few years or so. And the requirement basically says, okay, right, how much frequency do you have to, what is a frequency drop that you have to rise through? What is the voltage drop you have to rise through? What is reactive power? What is ramping? So all those things. If you're coming to the system, you have to satisfy. You have to show that you're able to satisfy this requirement. Right. So for example, we have voltage as an example in the system. Okay. So if your voltage, for example, is larger than 59.5 hertz, then you have to remain connected to the system. Okay. You have to stay in the system. If the frequency is between 59.1 and 59.5, you can try to disconnect, and if you count 6 seconds, and the frequency still haven't recovered, then you can go, okay, you can disconnect. If the frequency suddenly drops to below 59.1 hertz, then you can immediately disconnect. Okay, So then for this, this is actually something close to what happened in Texas, right? So remember, in the Texas outage, in the Texas blackout, what happened is the system basically started load shedding. Right? The reason the Texas system started load shedding is they basically observed a frequency that was very, very low. They observed a frequency that was very low, was lower than 59. And if lowering 59, you have a big button, you can panic, and then you start shedding load. So my feeling is going forward, right? So since right now the wind is at the same scale, right? If the frequency is too low, you can just disconnect. So the wind is not really providing a lot of service when there are big outages happening in the system. So in a few years, we may see an update to the code that will require wind to stay at a lower frequency. And that may be a possibility. Similar to the voltage code we have, as we may require wind to trip out, let's say, at 58 hertz rather than 59 hertz. Okay, so these are the things that after a big event, we'll try to go in and determine what happened. Okay, so this can be done, actually. This can be done. So we have an island system. So thus you can think of a microgrid or actually island system like Hawaii system. So Hawaii has a lot of actually island systems. Or a microgrid, for example, the Snohomish PUD's microgrid. There, the frequency requirement is actually quite a bit more relaxed, or actually more, depending on which way you count. I guess frequency requirement is one cannot leave the system at 59 hertz, right? For an island system, with the requirement that one can only trip off if it drops to below 56 hertz. Okay? This is sort of what one can do. So my feeling is going forward that we'll see the bulk grid system trying to move in this direction. You basically try to use all these resources to keep the grid going, even when the frequency drops to below 59 hertz. Right? So this can be done, and this is, for example, done in an island system. So for completeness, this is so Europe and the US have fairly similar requirements, right? So it's just that their standard frequency is 50 hertz, whereas ours is 60 hertz. Okay, so you see this, right? So this is frequency. Then for voltage, right? So we'll cover voltage in more detail next rest of the class. So I think now is a good time to take our break, right? So let's take the 10 minutes break we have. So we'll come back at 1:27. Then we'll finish looking at voltage rises, right? So we'll take a 10-minute break. Okay, so let's get started again. Sorry, I still haven't finished grading the midterm yet. I'll finish grading by the end of this week. Right? I'll finish grading by the end of this week. So now maybe a good time to talk about the final. Right? So if you look at the final for our class, our final is right now on the 18th of March. Right, so the format will be very similar to the midterm. So, out in the morning, due at midnight on the 18th of March. Anybody with more than 2 finals on that day? Right, so if you have 2 finals on that day, including this one, then there's not much we can do about that conflict. It's hard to avoid that. But you have 3, we can try. So if there anybody sort of have 2 other finals on that day, March 18th. Okay, so if you have 3 finals, for the people with 3 finals, can you please contact me? And then we can work out a different date for you to take the final. Okay, so the guidance is that, 2 is, sometimes there's just a course that lines up that way. You have 3, that may be too much, especially given all these are remote and some of them, maybe take home. So if you have 3 finals, please let me know. If you have 3 finals on March 18th. Right, so so you have 2, including this class, then that's, that's sort of normal in some sense, right? Depending on which class you choose, they may fall on the same day, but that's fine. If you have 3, then let me know, and we're trying to avoid that. Chase says, does people know when the 458 final is? Anybody know what class is it? Okay, so this is something try to figure out basically, right? So if you have this kind of conflict, again, if you have 3 on the same day, let me know. We can work out alternative date, but you do have to let me know this fairly soon. Right, we have about a little more than 2 weeks to go. Right, so if you have this type of conflict, please do let me know. We can adjust it, but the requirement is we do have to do it in that week. Right, so we do have to do it in that week. So, so if you have conflicts, let me know. If not, then the final will be very similar to the midterm. Will be, just covering the material we cover after the midterm, right? Covering that material. Right. Okay. So continuing with voltage rise through, low voltage rise through. So basically, low voltage rise through is similar to frequency, except that the voltage has a more defined shape. Okay, except the voltage has more defined shape. What I mean is we can think of the following, right? So for a wind turbine, are you more sensitive to frequency, or are you more sensitive to voltage? Think of type 3 and type 4. Which one are you more sensitive to? Okay, right. So think of the type 4 turbine, right? So would type 4 turbine care what the system frequency is? Does the type 4 turbine care? What frequency we operating? Think back to the circuit for type 4. Right, so type 4, you basically have a generator, then a AC to AC converter, right? Essentially AC to AC converter. So for a type 4, no, you're not very sensitive to frequency. You can, change your frequency at the output of your converter to match the system. So whatever the system frequency is to you, you're not particularly sensitive to that frequency. Okay? But you are sensitive to voltage, right? There's not much you can do about the grid voltage. That will create, different power flows in your circuit. Whereas frequency, you essentially have an isolation stage because you're power electronics. Whereas voltage, you're more sensitive, right? So you're more sensitive to the voltage in the system. So when we talk about voltage rise through, normally the voltage rise through looks something like this. So what the voltage looks something is you have this type of curve. What this type of curve means is this is point of interconnection voltage, right? So this is requirement. Right? So what this is basically anything, right? So this is, in some sense, this is sort of the worst case. So this is, in some sense, the worst case the turbine has to rise through. So basically, so you don't have to rise to arbitrary voltage profiles, right? Because of the way that voltage works, as if you see something, right? So for example, you do not need to survive this kind of profile for very long. You don't need to rise through this. Right? As a turbine, you can expect that if your voltage drops, will stay there for some time, then will start to rise again. So when you're designing a turbine, it turns out riding through a voltage that sort of just dips for a very long time. Turns out that's quite hard. That's sort of complicated. That's hard to do. So when your turbine design, basically the low voltage requirement you get is to say, okay, this is kind of curve we expect you are able to survive. And this turbine, this curve, right, basically has 3 stages. One is this is a fault, right? So at this point, we have a fault in the system. Some fault happens. You see a voltage drop. You see a big voltage drop. Then we'll stay at some minimum voltage for a little bit of time. Then the fault gets cleared and you sort of slowly ramp up. Okay? And this is the amount of time, this is this kind of curve you're faced with if you're a turbine. So the parameters we have in this is, right, we have to know what level you can recover to, what is the minimum voltage you have to deal with, how long does the fault clear, and how long does it take the voltage to rise. Okay, so this is the different numbers we have. So they all pretty much look like this. They just each area determines their own numbers. So this is a study you do. So some of you may have a question, if you go work for a system operator, what do you do? So this is one example of what you do. Okay, so you can go for a system operator. And what you do is your system wants to figure out all those different parameters that you want to require a turbine to operate with. Right? So this could be your job. As you do this kind of study, what should you set these numbers to be exactly? And this is one example of the outcome. Right? It's basically to say, so this is the US or the FERC requirement. This is to say the first drop can go to 0. Okay? You need to survive a fall that can go to 0. This can last for 200 milliseconds. Okay? This fall can last for 200 milliseconds and may take me 2 seconds to recover to about 0.85 per unit on voltage. Okay? So this is an example in the US. Okay, so this is one example we have, is to say that these are the numbers we use basically. And different places have different requirements. Basically, all kinds of different places have their own requirements. And this gets changed from time to time, but they all have shapes that look like this. So if you design a turbine, when you simulate the turbine, you have to design the turbine subject to the requirement of the particular system you install. Some may be more stringent than others, but you have to make sure you follow this requirement. So what it means is actually this. What means exactly this, right? So this is a requirement, right? So remember, this is a requirement. This is not the way the actual voltage works, right? This is just saying this is some requirement that you have. So for example, if you're a turbine, you may see an actual voltage that's something like this. This is actual voltage. Right? So the fault wasn't that bad. You did not go to the minimum, and you recovered. Right? You recovered, then you slowly rise. This means that you have to rise through this. This is the turbine has to stay on, okay, for this kind of rising. Right. So if the actual voltage at your terminal looks something like this, you have to rise through this. You have to stay on, right? Because this is sort of above the requirement for low voltage to rise through. Then another case that can happen is the actual voltage looks something like this, but doesn't recover. Then at this point, then the turbine can trip offline. Okay. So this depends on the exact wave set. Okay. So any question about this before I answer the question in the chat? Okay, so this is locally you measure in your turbine, you measure your voltage. You basically you have an internal mechanism trying to measure this and trying to you'll trip once this. If the voltage is worse, in the worst case you have been prepared to. Okay. Right. And so this is the right do. And this is actually important. You have to keep track of this. Because whenever you have outage, you actually this can be audited. You have to show that you perform low voltage rising. Okay, so you need to keep track of this. So Seth asked a question in chat is, why is there a step in Scotland's requirement? So let's look at this one. This means the red line, this step function here. So this step is basically you have to go back to 0.85 after 2.5 seconds. That's a requirement. So basically says the worst case will not be so bad that you're below 0.85 per unit after 2.5 seconds. This is what they believe of their system. Right? They say our voltage can recover after this much time to 0.85 per unit. This is sort of their belief of their system. Right, so the way to read this curve is right? So for example, if you look at Canada, right, the purple line is Canada, this Canadian line. This requires a lot from your wind turbine, right? This requires a lot from your wind turbine because it takes a long time to rise to the steady state voltage, right? And so you can drop pretty low to 0. So if you are able basically to satisfy the requirement, Canada's requirement, you can satisfy others. Right? So the way to read this curve is the lower right, so the right and lower corner is harder for the turbine to follow. Right? So this is harder for the turbine to follow. Right? Because for all the voltage that happen in this area, you have to be able to rise through. Right? Whereas for the one, for example, the black line, right, which is USA line. Now this is much, for the wind turbines, it's easier to satisfy the requirement, the US requirement, right? Because anything that satisfies Canada's requirement satisfies the US requirement. But different countries have different requirements. And depending on where you sell your turbines, you have to show different kind of performance capabilities. Okay. Any other questions about this? Okay, so if you look at this Vrt compliance, so this basically says, if your voltage is above this curve, you have to stay on all the time. If ever gets, below this curve, then you're done as a generator. You can trip. Okay? You're not penalized for tripping. So this is a actual measurement. This is actual measurement of a system. Okay, so we can recreate this in the lab. So what we did is we created a fault, a low voltage fault. And then if your turbine just cuts out, then you stay off. You never come back on. Or if you can do low voltage right through, the fault clears at this time, then you actually recover operation. You can recover this operation. You stay connected to the system. Okay, so you do see, for different turbines, you do see this kind of, right, for different turbines, you see sort of having this low voltage rise through capability is important. Right? And physically, the way to do this is you need to be able to dump mechanical power. You need enough different devices in your circuit to get rid of additional mechanical power. So if you have resistors, you can burn power that way. If you have a storage, you can charge your storage. But there are basically just as stay on when the voltage is low. So you have to divert power somewhere else. As long as you can do that, you can recover when the fault is clear. Right. So this is basically control action is you just keep measuring the voltage, basically, right? So this blue curve is given when you design the turbine. This is again something you hard code into it. And you keep measuring to see if the actual voltage is above this line. If it's above this line, you can keep, you keep going. If it's below, you can. If it's below, you can sort of you can just trip. Okay, this is sort of the internal operation in a turbine. Right, so then the protection of the next is we'll finish this by looking at the actual mechanisms to do this. Right, let's look at the actual mechanism that we can do this with. So this is the same thing as before. So actual mechanism, for example, if you look at a type 3 W-fed induction generator, right? For type 3 is if you have a fault here, right? That means this thing looks like pretty much like a ground to you, right? This thing looks like a ground to you. Then what you should do, right? Then what you should do is that you open, right? What you do is you open the connection as you open the connection of the AC-DC line converter, then you basically have another current pulled off the capacitor. So you provide another path of current flow from the capacitor. And this is another direction where you can route current. Okay? So this is sort of another direction you want to route current to go, right? So this is the type 3 we have. And basically all comes down to sort of figuring out where does current go if there's a fault. Okay? So in type 3, we're going to make the current go through this capacitor. In some, in type 4, you can have a resistor or you can have another exciter control that's inside the system. Right? But this is the type 3 we have. Okay, so you basically have an inductor generator and you pull current out of this capacitor, right? And that will help you to maintain the voltage also on the induction generator. Okay, so this capacitor is an important capacitor, right? And so sizing this capacitor is an important job when you're designing this type of turbines. Okay, so there's a lot of actually details going to all this kind of design. Right, so another way you can do is you can ramp wind turbines. Right, another thing you can do is you can ramp wind turbines. So this is more of a physical ramps in the wind turbines. Okay, so another way you can do this kind of control is you physically ramp the wind turbines, but then this is on a slower time scale. So the first 200 milliseconds, you won't have time to do this. After that, you may be able to ramp your wind turbine, ramp up, basically ramp down your wind turbine. Okay. So the idea is power electronics will have you to survive the first initial hundreds of milliseconds. Then the physical controlling the turbines can kick in and they can help you survive basically when you are slowly recovering, right? When you're sort of slowly recovering in this kind of picture, then the mechanical controller in your turbine can take over. Mechanical controller can take over to help you to slowly ramp up. Any questions about this? Okay, all right. So if not, let's go to look at a little bit of solar and storage for our next topic. All right, so again, I have to leave at 2 because to meet with a seminar speaker. So in the next 10 minutes, I want to look at sort of solar and storage to get us started, and then we'll dive fully into storage next class. So if you look at solar and storage, so basically we'll use solar to introduce storage a little bit just to have a change of pace. Okay, so our solar and storage, this is more of a change of pace for our solar. So this change of pace is, so you see actually a relationship between storage and what we cover quite quickly, quite soon. So this is a map of solar generation. It's not unexpected. This is where solar is, right, in the US. And then basically solar works through an inverter. Right? So the inverter that converts AC to DC. That works, that sort of makes solar, converts solar energy to power everything else. Okay? So in our class, we'll care about photovoltaics. Okay? We'll care about photovoltaics. Do you know some other kinds of solar? So photovoltaics are the, I guess, a common type we see. You see on the roof, it generates power by converting basically of a photon, striking a semiconductor that creates current, and then current creates power. Do you know other types of solar? Solar, right, solar thermal, right, or solar water heating. That's basically concentrated solar. So what this does is these are mirrors, what you see, and they heat up the thing in the, right, they heat up this, and you have something, typically not water. You want something with a higher specific heat capacity, but some other, for example, salt is something that's often used. It turns out you can melt salt, and that can retain a lot of heat. But this kind of concentrated solar is let's heat that up, and then use that heat to generate power down the line. That is not what we will talk about. Okay, so what we talk about has not much to do with concentrated solar. It's different technology. What we care, everything we say is more about this sort of solar PV, photovoltaics. Okay. And this is sort of more common one because this is the one you can build on your house, right? Or on top of our own campus buildings, you have this kind of solar. Okay. The main issue between solar and even wind is you have a mismatch between supply and demand. Right? So if you look at our demand, a typical demand curve or an aggregate demand curve, if this is 0 hour, this is 24 hours, then our demand curve looks something like this. Okay, so this peak is normally 7 p.m. or so. Okay, so this is normally the 7 p.m. peak. So this is our typical day curve, and this is about 4 p.m. Okay, so this is our 4 a.m. sorry, demand curve. If you're a grad student, your curve may look much different than this, but if this is the aggregate curve we have in the US. Okay? But then if you look at solar, what solar does is the production of solar, right? Definitely happens only in between these two times, right? So this is solar, and this is demand. Okay? So there's always a mismatch between solar and demand, pretty much. Right? For most of the places you look at, there's always a mismatch between solar and demand. And this creates a very famous California dot curve. Okay, so if you have seen this curve many times, I apologize, but you haven't seen this curve. What this curve shows us, if you look at 2013, okay, it's relatively flat during the day, relatively flat during the day. But as we have more and more solar coming to the system, then the curve starts to dip around the middle of the day because this is plotting solar as negative load, right? So this is a net load plot. This is the load minus solar. Okay? Because we have more solar during the day, you have this sort of huge sharp dip in the middle of the day. And this creates problem because this creates huge ramps that we see in our system. Okay, we see huge ramps, right? For example, this is the day high price. You can think of this as similarly representing. So this is the actual price we're showing. So this is dollar per megawatt hour. But you can think of this as proportional to net load. So this is very much proportional to that net load. Then what you have is you have big drops and the big ramp, okay? Because when solar starts kicking, you have a big ramp downwards. When solar, when at night comes, you have a huge ramp upwards. And this has nothing to do with uncertainty, actually. These are predicted. Okay, this is not unpredictable. This is very well predicted. These ramps are coming, right? So this is predicted, but it just, what do we do about it? Right? So ramps are coming. What do we do about it? So this is, similar to actually to the ride through that one generator has to do. As what you're afraid of is you're afraid of this sort of sharp ramps in the system. If the ramp is smooth, you can sort of slowly adjust your system to go along, follow it. But when things are this sharp, right, then you have to something has to happen, right? Basically, something has to balance the system and take care of these reps. Okay. So right now, these are taken care of by traditional thermal generators. Basically, what you do is when the rev happens downwards, you pay generators to turn off. Right? You pay them so they turn off their generation. Then when the ramp happens upward, we have these sort of big up ramp. You pay them a lot to kick back into the system to provide this generation. And this for conventional generators, you have to pay them for, in essence, both ways, right? So then the hope is, does storage help, right? Can we use storage? Does storage help, right? So, these are predicted. So it's not like you have to guess what happens for your storage. So these are predicted. And the question is, can storage help? And this extends to wind as well as solar, right? For wind is, for example, if you have to do low voltage ride through, or if you have to dump power somewhere for 1 second, the question is, can we find the storage, right? For wind is, instead of burning power through some resistors, can we use storage? And for solar is, if we know these things will happen, can we use storage instead of paying conventional generator to provide this kind of flexibility? Okay, so this is actually not a trivial question to answer. Right? In your mind, you may think, okay, obviously storage is the answer. Right? Obviously, sort of free money for the storage. Right? You can charge when the down ramp happens. People, you have very low cost to charge. And when the up ramp happens, you can make a lot of money, right? Because there's up ramp happening. So there's actually not that simple in practice to do this. And that has both to do with the technology we have for storage and the sort of this temporal nature of storage. It's quite different than other things we have in our system. Okay, so we'll stop here today because I need to go at 2. But next class, we'll get into storage technology. We'll look at, what different technology are there, what's a benefit, what's a drawback of each technology. And then we'll go into how do we algorithmically think about storage, right? How do you write equations with respect to storage? Okay, right, with that, thanks. So there's homework's due tomorrow. And then I will see you on Thursday. Thanks.